Okay, in this series, what we're going to do is find power series forms for similar functions to that of 1 over 1 minus x. So let's quickly remind ourselves that our first power series representation of a function is for the function 1 over 1 minus x. And that was just the series from n equals 0 to infinity of x to the n. And remember, this series only converged for x values that were less than 1 in absolute value. So the first idea I want to introduce us to is basically using this particular series and function to figure out other power series representations for functions very similar to 1 over 1 minus x. And the idea I want to draw us to is this idea of a stencil, just like we had in art class. And this idea of a stencil is we're going to take a look at this function, 1 over 1 minus x. But instead of looking at that minus x term, we're going to replace it by open parentheses. So in other words, our stencil, we're going to replace all the x terms in both the function 1 over 1 minus x and its associated power series with open parentheses. And the idea is going to be that, well, whatever goes inside those blue parentheses inside of 1 over 1 minus something is exactly what we're going to put inside the parentheses in our power series. So let's do a couple examples of using this stenciling idea. So if we have a series, we have a function, 1 over 1 plus x squared, and we want to find its power series representation. What we need to do is look at this through the lens of a stencil. So if we rewrite our function, 1 plus x squared, well, what we need to get it into is the form that's similar to this stencil up here. In other words, we need 1 over 1 minus something. And the idea is going to be, how can we get this function into that form of 1 over 1 minus something? Well, we know we need a 1 minus. So inside those blue parentheses, since we need a 1 minus something, we could extract a minus sign so that we get minus times a minus gives us that plus that's seen over here. And well, instead of an x, we have an x squared. So inside of those parentheses, we can just put that minus x squared. And well, when we write that as a power series now, we take everything inside those blue parentheses and just raise it to the power of n, like our original power series. So inside these blue parentheses, we just stick our minus x squared. So in other words, one over 1 plus x squared, we can rewrite as 1 over 1 minus the quantity negative x squared, where those blue parentheses are our stencil. And everything inside those blue parentheses is just where we placed x's before inside of our power series. So we have minus x squared all raised to the nth power, which we could do a little bit of algebra on if we were so inclined, and get that this is, well, minus 1 to the power of n times x squared to the power of n, which we can then just rewrite as the series from n equals 0 to infinity of minus 1 to the n times x to the 2n. and that is the power series representation of the function 1 over 1 plus x squared. Now, this power series I'm circling and its function 1 over 1 plus x squared, we don't have to commit that to memory, because the only thing that we needed to get to this was the fact that our original power series, 1 over 1 minus some quantity, is equal to the power series from n equals 0 to infinity of that blue something raised to the nth power. So as long as we can remember this ladder, 1 over 1 minus something, or 1 over 1 minus x power series, we can develop that stencil to get power series that are very similar to it. Let's do another example. So this is the power series of this is the function 1 over x plus 2. And we want to get this in, we want to find a power series representation. So, again, what we're doing is calling upon our stencil. Hey, 1 over 1 minus something gives us that power series from n equals 0 to infinity of that something raised to the nth power. And this is coming from that function 1 over 1 minus x. So let's take this function that we're given and start moving it towards that stenciling form. So we have that this is 1 over, let's switch the denominator order to get first that number first. Well, we're not quite in that form because this 2, we want that to be a 1. We don't want that to be a 2. So we get to do a little bit of algebra here. So what we can do next is pull out a factor of 2 from everything in the denominator. So if we do that, we get that this is 1 over 2 times the quantity 1 plus x over 2. So if we multiply that 2 into those parentheses, we just get back to the thing we had before. And now since we have the product of two things in the denominator, well, we can just pull that 1/2 out in front. And now we have 1 over 1 plus x over 2. And we're getting there. We now have this leading order of 1 in our function, just like we have in our stencil. So we're getting closer to that stenciling form. The next thing we can do is, well, let's change that positive sign into a negative sign by doing 1 over 1 minus. Now here's where that stencil comes in. A minus sign. So we have minus minus would give us the plus. And inside those blue parentheses, we can place that x over 2 as well. So what this looks like now is basically what we're there for our stenciling form. Inside those blue parentheses, we can place a minus x over 2 and raise that to the nth power. And the last thing we need to do is, well, we have that coefficient of 1/2 before that function, so that coefficient of 1/2 needs to go in front of that power series as well. So in conclusion, for this problem, this 1 over x plus 2 function has a power series form of 1/2 times the power series of n equals 0 to infinity of the quantity of negative x over 2, all raised to the nth power. And of course, we could do a little bit more algebra on this if we so desired. And if you're asking yourself why you might consider doing a little bit more algebra, in other words, we can pull out a minus 1 to the n, and then we are left with this term of x over 2 to the nth power itself is just because, well, you know what? If we want to differentiate or integrate this function, it's a lot easier to just isolate the n dependent or the x dependence by itself. So that note, we could even take it a step further. The power series from 1/2 times the series n equals 0 to infinity of -1 to the n, x to the n, over 2 to the n. And, well, we could bring this other factor of 1/2 inside of this series, and it could combine with this 2 to the n. So the last step that we can do is rewrite this power series as n equals 0 to infinity of -1 to the nth power times x to the n all over 2 to the n plus 1. Because remember, just as a quick aside, if we have the product of 2 to the first times 2 to the n, we add the powers. So this would be 2 to the n plus first power. Let's do one more example here. So this is, again, find the power series representation of a function. So in this case, let's consider this function of x cubed all over, you know what, 1 plus x squared. Or actually, we already did 1 over 1 plus x squared. Let's do just 1 over 1 plus x. And again, this is find the power series representation. Well, we know the stencil that we're after is of the form 1 over 1 minus something in blue parentheses, and that we're going to be able to set equal to the power series from n equals 0 to infinity of whatever's in those blue parentheses raised to the nth power. So let's try to move this function that we're given into that form. And the first thing is, well, we don't want that x cubed sitting in the numerator. We want just a 1 in that numerator, so we can bring that x cubed out in front and think about multiplying it onto that function, 1 over 1 plus x. And, well, let's move towards that stencil now. So we have x cubed multiplying our fraction, 1 over 1 minus a negative x. And that minus minus would give us that original plus in that denominator. So we can rewrite this now as the power series from n equals 0 to infinity of, remember, whatever's in those blue parentheses, in this case a minus x, raised to the nth power. And of course, we could try to simplify this a little bit. We have the x cubed out in front. This is the series from n equals 0 to infinity. We have a minus 1 to the n. We have this other x to the n term. And, well, you might be seeing where we're going with this. We could bring this x cubed term inside of the series, and it'll combine with this x to the n term. And what we'd be doing is multiplying every single term in this series by this x cubed. So when we go ahead and do this, we'll do this in 2 steps. What this really looks like for us is this minus 1 to the n. We have x cubed that was originally sitting out in front of our series times an x to the n. And since now we're multiplying 2 different quantities but with the same base and different powers, we can add those powers. So this now equals a series from n equals 0 to infinity of minus 1 to the n times x to the n plus 3. And that's equal to the original function that we had of x cubed all over 1 plus x. And remember, we shouldn't go ahead and memorize the power series of this particular function, as long as we remember how we got there. This stenciling technique is very powerful, where again, we started off with our function 1 over 1 minus x, and we replaced all of the x's in both the function and the power series by just open parentheses. So therefore, whatever we put into these parentheses, we could just move into the power series as well. Next, we're going to do some similar type of manipulation of finding series or power series representations of functions, except focusing more on kind of some calculus operations, integrating and differentiating to get different power series. Let's check it out.